Hello, my curious friend, and a very warm welcome to Deep Field channel. Tonight we will lift our gaze and sink it deep as well, toward whatever lies above and below our tiny cosmic home, this solar system we call our own, without ever having truly explored the neighborhood around it. We are going to uncover what inhabits that immense space, stretching perpendicularly to the plane where we live, as if the cosmos had kept its strangest secrets precisely on the floors nobody ever thinks to visit. I promise to try not to make the subject so fascinating that it robs you completely of your sleep, but I make no absolute promises when the universe is involved. But before we begin this vertical journey through the cosmos, I would love to know in the comments which corner of the world you are listening to me from tonight. And if laziness strikes, just leave a simple hello. It may seem like very little, but that small gesture tells YouTube that our space is welcoming and helps us bring more tired minds here to relax with us. If you enjoy our scientific journeys, leave your like and subscribe as well. And to those of you who are already part of our community, thank you so much. If you want to get even closer, consider becoming a channel member. Members get early access to videos before everyone else. The link is in the description. Now, wherever you are, find a truly comfortable position. Release your shoulders, relax your jaw. Let the weight of your body be completely supported by whatever you are lying or sitting on. If sleep comes, accept the invitation. Let us begin. There is a very simple mental exercise that very few people perform, even though it is completely free and available every single night. It is the exercise of looking at the sky and asking not what is out there in the direction your eyes point, but what is up there in the most literal sense possible. Not the stars you see, not the moon, not the planets visible to the naked eye, but what exists specifically above, in the way an architect would think, what is the floor above this building called the solar system? And then, in an inversion that seems philosophical but is entirely physical and verifiable, what exists below? This question seems simple. It is not. To begin answering it honestly, we first need to undo a very common misconception, one of those that seems obvious when you carry it but completely unravels the moment someone points it out. Most people think of the solar system as a sort of little ball floating in the vacuum of space, with no particular orientation, no up or down, spinning freely like a balloon in a windowless room. That image is understandable, even poetic in its own way, but it is wrong in a very specific and very revealing way. The solar system has an orientation. It does not float randomly. It exists within a larger structure that has shape, thickness, and direction, and within that structure our solar system occupies a position that can indeed be described with the words above and below, as long as we understand where that reference comes from. That larger structure is the Milky Way, our galaxy, and the Milky Way, contrary to what the name might suggest to someone who has never thought much about it, is not a diffuse and spherical cloud of stars scattered uniformly in all directions. It is extraordinarily flat. It has the shape of a disk, like a spinning plate, like an old CD, like those pot lids that children use to imitate shields in battle games. An immense disk with spiral arms coiled around themselves, with a denser and brighter center that we call the galactic bulge, and our solar system is inside this disk. This is what makes the original question so interesting. When we ask what exists directly above and below our solar system, we are asking what exists outside the plane of the galactic disk, in the directions perpendicular to that cosmic plate. We are essentially asking what exists in the attics and basements of our galaxy. Before continuing, it is worth spending a few moments with the scale of what we are describing, because the human mind was sculpted by evolution to deal with distances traveled on foot, by horse, by car, at most by airplane. The scales of the cosmos demand a different kind of attention, more like meditation than calculation. It is not about visualizing with precision. It is about feeling the weight of the number without needing to hold it completely. Our solar system, from the Sun to the edge of what we call the Oort Cloud, which is the most distant region where objects still exist that are gravitationally bound to the Sun, has a radius of approximately 1 light year. A light year is the distance that light travels in 1 year at 300,000 kilometers per second. It is a distance that defies any honest attempt at visualization. But even that colossal extent is tiny compared to what comes next. The Milky Way has a diameter of approximately 100,000 light years. That means if you could travel at the speed of light for 100,000 years, you would go from one edge of the galaxy to the other. And the thickness of this disk, the distance from the galactic midplane to where stars and gas begin to become truly scarce, is approximately 1,000 light years in the densest plane, with a more diffuse region that can extend for several additional 1,000 light years above and below. Our solar system is located about 26,000 light years from the galactic center, and in relation to the midplane of the disk, our position is slightly offset, like a grain of salt that fell almost at the center of a plate, but not exactly. We are a few dozen light years above the galaxy's midplane, slightly off-center, in a position that, as we shall see, is not static but oscillating. That last word deserves a pause. The solar system is not stationary within the galaxy. It moves, and it moves in multiple and simultaneous ways. It orbits the galactic center, completing one revolution approximately every 225 million years, at a speed of about 240 kilometers per second. But beyond that orbital movement, it also oscillates vertically, like a boat moving across the ocean but rising and falling with the waves. This vertical oscillation is one of the most hypnotic and least known facts about our cosmic existence. The solar system descends toward the galaxy's midplane, crosses through it, continues to the other side, rises, decelerates, stops, descends again in a cycle that lasts tens of millions of years to complete each semicircle. It is like an extraordinarily slow pendulum, moving perpendicular to the galactic disk, while simultaneously advancing in orbit around the center. What this means concretely is that the answer to what exists above and below our solar system is not a single and fixed answer. It changes over geological time. Tens of millions of years ago, when dinosaurs were not even a distant idea in the fossil record, our solar system was in a different vertical position relative to the galactic plane. And tens of millions of years from now, it will be in yet another different position. But even accepting this dynamic nature, we can ask the question more specifically: what exists above and below now? Or more precisely, what exists in general in the regions that are outside the galactic plane, where our solar system periodically visits during this eternal oscillation? The answer begins with something that seems like nothing but is not nothing. Above and below the plane of the galactic disk exists what astronomers call the galactic halo. The word halo carries a connotation of purity, of lightness, of a nimbus, and in a certain sense, this word was well chosen because the halo is a much less dense region than the disk, far fewer stars, far less gas, far less interstellar dust. If the galaxy's disk is a city with buildings, lights, and movement, the halo is the open countryside around it, with a few scattered houses, silence, and a darkness that seems definitive. But within this apparently empty vastness, things exist: old things, slow things, silent and extraordinary things. The first of these are the halo stars. They exist, but they are rare and have a characteristic that fundamentally distinguishes them from the stars that live in the disk like our Sun. The halo stars are old, not old in the way we call a 19th century building old. Old in the sense that they formed in the first billions of years of the universe, when the cosmos was young, hot, and composed almost entirely of hydrogen and helium, the two simplest elements that exist. This matters for a specific reason. The stars that live in the galactic disk, like the Sun, formed from material that had already passed through the interiors of previous stars. The universe works like a recycling factory. Stars form, live, die, and scatter into space the heavy elements they forged in their cores, elements like carbon, oxygen, iron, silicon. The next generation of stars is born from this enriched mixture. The Sun is, in this sense, a third or fourth generation star, rich in metals, as astronomers say, using the word metal differently than we do in everyday life. The halo stars, on the other hand, are first or second generation stars, poor in metals, born of a universe not yet enriched by the death of previous generations. They shine with a different chemical composition, and this difference makes them living documents of the most remote history of the cosmos. Observing a halo star is like reading a letter written before most words existed, and these halo stars do not distribute themselves randomly above and below the disk. Many of them group into structures called globular clusters, which are among the most beautiful and most ancient objects that exist in the observable universe. A globular cluster is a spherical and dense collection of hundreds of thousands, sometimes more than 1,000,000 stars, gravitationally bound to each other, orbiting the center of the galaxy in trajectories that take them above and below the plane of the disk. Like satellites in highly inclined orbits, the Milky Way possesses more than 150 known globular clusters. Some of them are above the galactic plane, some are below, some cross the plane during their orbits. They are structures that have existed for more than 10 billion years. Balls of ancient stars floating silently in the outskirts of the galaxy, witnessing eras that the human mind cannot truly inhabit with imagination. But the halo is not composed only of stars and clusters. There is something more out there, something that astronomers can detect by its effects but cannot yet see directly, something that makes up the majority of the galaxy's mass and extends far beyond any star or gas cloud. Something that does not emit light, does not reflect light, does not absorb light the way ordinary matter does. This something has a name that carries all of its strangeness: dark matter. The galactic halo, the region that extends above and below the disk far beyond where any star shines, is fundamentally a dark matter halo. It is this invisible and mysterious substance that holds the galaxy together, that explains why the stars at the edges of the disk orbit as rapidly as stars near the center, when by classical physics they should orbit much more slowly. It is like discovering that a city has an invisible population several times larger than the population you can see, and that this invisible population is responsible for most of the structure and order of the place. Dark matter does not interact with light. It interacts only through gravity, and therefore it can be mapped indirectly by measuring how the light from distant objects is bent when passing near regions where it concentrates, or by measuring the orbital velocities of stars and gas around the galaxy. The result of these measurements is disconcerting and at the same time magnificent. The dark matter halo of the Milky Way is much larger than the visible disk. It extends for hundreds of thousands of light years in all directions, forming a kind of invisible sphere around the entire galaxy. The disk, with its bright stars, its spiral arms, its luminous center, is immersed within this sphere of matter that we do not see but that we feel through its gravitational effects. When our solar system is above or below the plane of the galactic disk in its periodic oscillation, it is still deeply within this dark matter halo. It always has been. It always will be. It is like realizing that the house where you live is inside a building whose walls are invisible but whose weight is real and constant. And it is precisely here, at this point where the visible and the invisible touch, where the matter we know floats within an ocean of matter we do not yet understand, that the deepest question of this entire story arises. If this entire structure, the disk, the halo, the clusters, the ancient stars, the dark matter, if all of this exists and interacts and moves, what provides the energy that animates this system? What drives the oscillation? What maintains the orbits? What made the disk form and continue spinning after billions of years? What is the source, the origin, the engine behind everything we have just described? This answer is waiting silently in the next layer of what we have to explore. Gravity has no color, it has no smell, it makes no noise as it works. It is the most productive silence in the universe, the force that never rests and never announces its presence, but that is present in absolutely everything that exists, from the atom to the supercluster of galaxies. And it is she, only she, who answers the question that was left hanging in the air. What moves all of this? Think of a glass basin full of water. If you place a drop of ink in the center, it will slowly spread in all directions, creating smooth, circular, almost hypnotic patterns. But if you tilt the basin slightly, the water begins to move toward the lower side and the ink goes along, carried by the slope of the space it inhabits. The galaxy works in a similar way, except that the basin is space-time itself, and the ink is matter, and the slope is caused by the presence of mass. Where there is mass, space curves. Where space curves, matter moves. Where matter moves, more matter accumulates, and this cycle feeds back with a patience that no human mind can truly measure. Gravity, then, is the source, but this answer, however precise, is also incomplete on its own, because gravity does not merely pull. It also organizes, separates, compresses, accelerates, and in some cases destroys. To understand how it does all of this so orderly within a galaxy like the Milky Way, one must understand the laws that govern its behavior, and those laws have history, have names, have human faces behind them. Imagine that you are on top of a hill and roll a stone downhill. The stone accelerates. The further it goes down, the faster it gets. If there were nothing to stop it, it would continue accelerating forever or until some other force came into play. What you just imagined is the most basic principle of gravitational dynamics. In a gravitational field, objects in free fall gain kinetic energy as they lose potential energy. The sum of the two remains constant. This is conservation of energy, and it is one of the most fundamental laws of physics, so fundamental that it was not so much discovered as perceived, like someone who always knew how to walk but only learns the name of the act when someone explains it. Gottfried Wilhelm Leibniz in the 17th century used the term vis viva to describe what we call kinetic energy today. He was in dispute with Isaac Newton about the nature of motion and force, an intellectual fight that lasted decades and involved monumental egos and furious correspondence across the English Channel. Leibniz believed that what mattered in motion was the product of mass times velocity squared. Newton argued for a different quantity. Both were partially right, and the synthesis between the two views took generations to complete. But the central point of this story is not who won the dispute. It is that two men living on separate continents, without computers, without modern telescopes, without satellites, managed to perceive something about the nature of the universe just by observing balls rolling, pendulums swinging, and planets moving. Physics was born from dedicated attention to what was already visible. Newton, of course, is the name most associated with gravity. His law of universal gravitation, published in 1687 in the Principia Mathematica, was a moment of rupture so absolute that it is difficult to describe without using the word miracle. He said that any two bodies attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Written like this, it seems simple, But what this sentence means in practice is that the same force that makes an apple fall from a tree is the same force that keeps the moon in orbit around the Earth, that keeps the Earth in orbit around the Sun, that keeps the Sun in orbit around the galactic center. The law does not change. The scale changes. The principle remains. To feel what this means, think of a stone tied to a string. If you spin the stone in circles above your head, it stays in orbit around your hand. Release the string and it flies in a straight line. What kept the stone in circular motion was not a force pushing it inward. It was the tension of the string, a centripetal force, constantly directed toward the center of rotation. In the solar system, in the galactic system, this string is gravity. The Sun pulls the Earth toward itself, and the Earth, instead of spiraling into the Sun, is moving fast enough sideways that the fall transforms into a permanent curve. It falls eternally and never arrives. That is what we call an orbit. The same happens with the Sun around the galactic center, except that the galactic center is not simply a point. It is a region of concentrated mass, dominated by a supermassive black hole that astronomers call Sagittarius A star, with a mass equivalent to approximately 4 million solar masses. The Sun, with its entire planetary system, orbits around this center at a speed of about 220 kilometers per second, taking roughly 225 million years to complete a single revolution. To this period, astronomers give the name galactic year or cosmic year. Throughout the entire existence of the Earth, our planet has completed just over 20 of these full cycles. But Newton's law, however powerful, has a limit. It describes with absolute precision the gravitational behavior at scales we can test, measure, and verify. At extreme scales, near very massive objects, or when velocities approach the speed of light, it begins to fail. Not because it was wrong, but because it was an approximation of something deeper. And that something deeper took another 200 years to appear. Albert Einstein, working in Bern at the beginning of the 20th century, realized that gravity was not simply a force like the others. It was a geometry, a curvature. Imagine a bedsheet stretched horizontally. Place a bowling ball in the center and observe what happens. The sheet gives way, forms a depression, a funnel. Now roll a marble near the bowling ball. The marble does not go in a straight line. It follows the curvature of the sheet, tracing a curved trajectory around the depression. It is not being attracted by an invisible force. It is following the most natural possible path within a space that has been deformed by a massive presence. This is general relativity. Einstein published his theory of general relativity in 1915. And it forever changed the way we understand space, time, and gravity. They are not three separate things. They are dimensions of a single structure called space-time, mass curve space-time. Objects in motion move along the curvatures of that space-time. What we perceive as gravity is the result of following the most natural path within a space that is not flat. For the Milky Way, this means that the entire structure we described earlier, the disk, the central bulge, the halo, the dark matter, all of this is not simply floating in space. It is curving the space around itself. And every part of the galaxy, every star, every gas cloud, every concentration of dark matter is responding to the curvatures created by all the other parts. It is a gravitational conversation of almost unimaginable complexity, conducted in silence over billions of years. The fundamental imbalance that makes all of this work is not gravity itself. It is the competition between gravity and motion. Gravity wants to pull everything to a single point. Motion wants objects to continue in a straight line. This conflict between collapse and expansion, between contraction and rotation, is the engine of all structures in the universe. A gas cloud that had no rotational motion at all would simply collapse upon itself until becoming a star or perhaps a black hole. A cloud with too much rotational motion would scatter into space without ever forming anything. The universe is full of structures precisely because it found, repeatedly, this delicate balance between the two tendencies. Johannes Kepler, before Newton, had already empirically perceived this balance in planetary orbits. Working with the extraordinarily precise data of Tycho Brahe, a Danish astronomer who spent decades measuring positions of planets with the naked eye with unprecedented precision in history, Kepler discovered that planets do not move in perfect circles, but in ellipses. He discovered that they move faster when they are closer to the Sun and slower when they are farther away. He discovered that there is a precise mathematical relationship between the size of a planet's orbit and the time it takes to complete it. He did not know why, he just saw the pattern. Newton, decades later, provided the explanation. This sequence, observation without explanation, followed by explanation without complete observation, followed by unification, is the internal rhythm of physics, and it continues to this day. Einstein unified Newton with the geometry of space-time. But Einstein's theory, in turn, does not satisfactorily explain the behavior of dark matter, nor of dark energy, which seems to be accelerating the expansion of the universe. There is something even deeper waiting to be discovered. What gravity does within the Milky Way, then, is at the same time simple and immense. It collapsed clouds of primordial hydrogen to form the first stars. It grouped those stars into clusters, and those clusters into larger structures. It flattened the distribution of gas and stars into a disk because angular momentum, that tendency of rotating objects to keep spinning, resists collapse in the orbital plane but does not resist collapse perpendicular to it. That is why the galactic disk is much thicker in the vertical direction than it is shallow in the plane of rotation. Angular momentum is the formal name for something you already know. When an ice skater pulls their arms close to their body during a spin, they accelerate. When they extend them again, they decelerate. The rotation speed changes, but the amount of angular momentum remains the same. This principle, called conservation of angular momentum, governs everything from the spin of a ballerina to the formation of accretion disks around black holes, passing through the flattened shape of the Milky Way itself. Vera Rubin, an American astronomer working in the 60s and 70s of the last century, noticed something disturbing while studying the rotation of the Milky Way and other spiral galaxies. The stars at the outer edges of the galaxies were moving too fast. According to the laws of Newton and Kepler, objects farther from the center of mass of a system should move more slowly, just as the outer planets of the solar system move more slowly than the inner ones. But the stars at the edges of galaxies moved at almost the same speed as the stars closer to the center. This was only possible if there was an enormous amount of invisible mass distributed through the galaxy's halo, keeping the velocities high. It was the strongest dynamical evidence that something existed there, something that did not emit light but exerted real and measurable gravity. Vera Rubin dedicated decades to accumulating this evidence. She measured rotation curves of dozens of galaxies, and in all of them the pattern repeated. She did not receive the Nobel Prize for this work, an omission that the scientific community widely laments to this day. But her observations permanently transformed cosmology and made dark matter not just an exotic hypothesis, but a structural necessity, a piece that the puzzle simply does not close without. And now, with all of this in mind, think of a single cloud of interstellar gas within the galactic disk. It floats, apparently motionless, within a spiral arm, but it is not motionless. It is rotating around the galactic center. It is oscillating slightly above and below the midplane of the disk. It is suffering the gravitational pressure of neighboring stars, of other clouds, of the disk itself. At some point a disturbance arrives, perhaps the pressure wave from a nearby supernova explosion, perhaps the passage through the denser spiral arm. The cloud begins to compress, it begins to heat up, it begins to collapse under its own weight. A star is born. This process happens constantly throughout the Milky Way. Stars are born, live for millions or billions of years, and die. Each death releases energy, throws enriched material back into the interstellar medium, disturbs neighboring clouds, and can trigger the birth of new stars. It is a cycle, but not a static cycle. It is a cycle that transforms the chemical composition of the galaxy over time, that alters the distribution of mass, that subtly modifies the very gravitational curvatures that govern the system. What happens when this cycle, this single birth and death of a star, repeats not once, not 1,000 times, but hundreds of billions of times, distributed across dimensions the mind cannot visualize, across a time we cannot feel, all at the same time, all interacting, all affecting each other through this invisible gravitational field that permeates everything? What emerges from this incessant cycle is not the chaos one might expect when contemplating so many simultaneous forces acting in so many different directions. What emerges is something that physics calls structure, but that everyday language would better recognize as pattern, as order that no component chose but that all obey. The Milky Way, seen from outside by a hypothetical observer floating above the galactic plane, would not look like a uniform mist of randomly scattered stars. It would look like a shape with proportions, with symmetries, with denser regions and sparser regions, with arms that curl from a thickened center like foam that slowly spins on the surface of a viscous liquid disturbed by an invisible spoon. This spiral appearance is not decorative, it is functional. It reveals how matter organized itself over billions of years under the influence of gravity, rotation, and the internal pressures that the galaxy's own content exerts upon itself. The disk that makes up most of the Milky Way has a relatively modest thickness compared to its diameter, and the solar system inhabits this disk, immersed in its thinnest layer, the so-called thin zone of the stellar disk. This position is not arbitrary. It is a direct consequence of how the original gas that formed the galaxy flattened as it spun, exactly like pizza dough flattens when spun in the hands of someone experienced, the rotation speed creating a centrifugal force that distributes matter outward and downward relative to the axis of rotation. The flattening of the disk is one of the most elegant phenomena in galactic dynamics. A spherical gas cloud that begins to spin cannot maintain its sphericity for long. The rotation creates a preference of plane. Particles moving with velocity components perpendicular to the plane of rotation tend to collide with other particles and dissipate those components, while the components in the plane of rotation are preserved by conservation of angular momentum. The inevitable result is a progressive collapse toward a plane. The entire galaxy, with all its complexity, with all its gases and stars and magnetic fields, is expressing this fundamental physical principle on a colossal scale. But the disk is not perfectly flat. Here begins one of the most surprising discoveries of 20th century astronomy. The disk of the Milky Way is slightly curved, like the brim of a hat that someone carelessly bent in one direction. This curvature, called the galactic warp, is more pronounced in the outer regions of the galaxy, far from the center, where the gravitational force of the nucleus is weaker and matter is more subject to external disturbances. The regions of the Milky Way that are above the plane in one direction are below the plane in the opposite direction, creating a gentle asymmetry that runs the entire extent of the disk like a wave frozen in time. The solar system is close enough to the galactic center not to dramatically feel the effects of the warp, but the existence of this curvature reveals something important about the nature of the galaxy as a dynamic object. The Milky Way is not a rigid and static structure. It is a living system in tense equilibrium, constantly disturbed by interactions with other galaxies, with the dark matter that surrounds it, with the gravitational tides that the larger universe exerts upon it. The warp may be, according to some hypotheses, the residue of a past interaction with a satellite galaxy, a gravitational scar that time has not yet completely erased. Within the disk, the organization into spiral arms adds another layer of structure. The spiral arms are not regions where there is permanently more matter. They are more like density waves that travel through the disk, regions where gas and stars are momentarily more compressed while the wave passes through them. An individual star like the Sun does not get trapped in a spiral arm forever. It crosses through the arms along its galactic orbit, entering regions of higher density and exiting them periodically over hundreds of millions of years. Each passage through a spiral arm is a different experience for the planetary systems that make this journey, because the arms are regions of active star formation, of more frequent supernovae, of more intense radiation fields. The Swedish astronomer Bertil Lindblad was one of the first to seriously think about how galactic spirals could be maintained over time in the early decades of the 20th century. The problem he identified is subtle but devastating for any naive explanation. If the arms were structures of fixed matter, they should completely wrap around the galactic nucleus after a few rotations, because the inner regions of the galaxy rotate faster than the outer ones. In a few billion years, the arms would have wrapped around themselves until disappearing. But the spiral galaxies we observe are abundant and seem to persist. Something keeps the arms. The solution arrived decades later, elaborated mainly by the astronomers Chia-Chiao Lin and Frank Xu in the middle of the 20th century through the density wave theory. They mathematically demonstrated that spiral arms can be stationary wave patterns in the galactic disk, analogous to sound waves in an elastic medium. The density wave propagates through the disk and matter flows through it, compressing as it enters and expanding as it exits. The pattern persists even though the individual matter that composes it is in constant motion. It is one of the most beautiful instances in astrophysics of how structure can exist independently of its specific components, like the flame of a candle exists independently of the specific fuel molecules burning at each instant. Perpendicular to the disk, the organization of the galaxy is radically different. Above and below the galactic plane, the density of matter drops rapidly, but does not cease. There is a stellar halo that extends for immense distances above and below the disk, inhabited by very old stars, the oldest in the galaxy, that formed before the original gas had time to flatten completely. These halo stars follow orbits very different from disk stars. Instead of orbiting more or less in the galactic plane as the Sun does, halo stars follow inclined elliptical orbits, periodically diving through the plane and rising far from it, like balls thrown at different angles that converge and diverge from the same central point. The distribution of these halo stars preserves memories of ancient events. When a smaller galaxy is gravitationally captured by the Milky Way and gradually torn apart by tidal forces, its stars scatter along the orbit that the smaller galaxy followed, forming stellar streams that can be mapped as faint threads of light distributed through the halo. These streams are dynamic fossils, records of the history of absorption and growth that the Milky Way has lived over billions of years. Some of the globular clusters that orbit the galaxy may be the surviving nuclei of dwarf galaxies that were captured and torn apart in the distant past. Globular clusters are themselves extraordinary structures in the large-scale organization of the galaxy. They are spherical sets of hundreds of thousands or even millions of stars held together by their own gravity, orbiting the galactic center in halo orbits. Unlike the loose stellar associations that exist in the disk, globular clusters are dense and gravitationally bound structures that resist disruption by tidal forces for billions of years. Their distribution around the Milky Way is approximately spherical and centered on the galactic nucleus, which was historically used to determine the position of the Sun within the galaxy. It was precisely this method that allowed the American astronomer Harlow Shapley in the early decades of the 20th century to make one of the most transformative discoveries in modern astronomy. By mapping the distribution of globular clusters in the sky and measuring their distances using variable stars as distance indicators, Shapley realized that the center of their spherical distribution was not near the Sun. It was very far away, toward the constellation Sagittarius, tens of thousands of light-years distant. The Sun was not at the center of the galaxy. It was in a peripheral position about 2/3 of the galactic radius from the center, a position that would later reveal itself to be typical and not special in any obvious way. This realization by Shapley was one of the most profound in the entire history of human thought about its position in the cosmos. Not only was the Earth not the center of the solar system, as Copernicus had demonstrated centuries before, the solar system itself was not at the center of the galaxy. Each stage of scientific understanding seemed to move humanity to a more peripheral, more common position, more embedded in structures much larger than any that could be perceived without instruments and careful reasoning. The large-scale structure that astronomers mapped throughout the 20th century reveals a galaxy with multiple concentric layers of organization. At the absolute center, there is a region of extreme density, with a concentration of stars so intense that the night sky seen from there would be incomparably brighter than the one seen from the solar system. Surrounding the center is a galactic bulge, an approximately ellipsoidal region with billions of ancient stars. From the bulge extends the thin disk, where star formation is active and where the solar system inhabits. The thin disk is wrapped by a thick disk, less dense and composed of older and chemically less enriched stars. All of this is immersed in the stellar halo, which in turn is inserted into an immensely larger dark matter halo, directly invisible but revealed by its gravitational effects. Each of these layers has its own chemical, dynamic, and historical properties. The thin disk where we live is chemically enriched because it has gone through many generations of stars that synthesized heavy elements and returned them to the interstellar medium. The stellar halo, by contrast, contains stars of much more primitive composition, made almost exclusively of hydrogen and helium, with only traces of the heavier elements. Because they formed when the universe was young and few generations of stars had yet contributed their nuclear products to the cosmos. The differential rotation of the galaxy, the fact that the inner regions rotate faster than the outer ones, creates tensions and patterns that influence the entire structure. The solar system completes one orbit around the galactic center in what astronomers call a galactic year, a duration of time so extensive that since the emergence of the first multicellular beings on Earth, the Sun has completed only a few of these full cycles. During each orbit, the solar system oscillates vertically above and below the galactic plane, like a carousel horse that rises and falls while spinning. This oscillation has a period of tens of millions of years and takes the solar system to altitudes of a few hundred light years above and below the midplane. Some researchers speculate that these passages through the galactic plane, when the solar system crosses regions of higher matter density and potentially disturbs the cloud of comets that surrounds it at the extremities, could correlate with periods of increased cometary bombardment of the Earth. The idea that mass extinction cycles in the fossil record might have a cadence linked to the vertical movement of the solar system in the galaxy is controversial and still without consensus, but it illustrates how the position of the solar system within the large-scale galactic structure is not irrelevant to the history of life on Earth. The galaxy is not a neutral backdrop. It is an active environment that the solar system crosses and that affects it in ways we are still learning to quantify. The picture that emerges from all of this is one of organization at multiple scales, where each scale is nested within the larger ones and influences the smaller ones. Individual stars organize into associations and clusters. The clusters organize into spiral arms. The spiral arms define the disk. The disk is inserted in the halo. The halo is within a much larger dark matter structure, and this entire hierarchy of structures exists in a dynamic equilibrium, never perfectly static, always adjusting in response to internal and external disturbances. What makes this panorama even more fascinating is contemplating how all this extraordinary organization, all this emergent geometry, all this hierarchy of patterns arose from relatively simple initial conditions. A young universe full of hydrogen and helium, subjected to gravity and time, produced all this complexity without any central planning, without any coordinating intelligence. Every structure we observe is the inevitable result of the laws of physics acting on matter over sufficient time. The order we see is real, but it is emergent. It arises from the bottom up, from the components to the whole, and is not imposed from the top down by some organizing will. However, there is an element that the simplest models of galactic formation could not completely explain. When astronomers calculated how the structures we observe could have formed starting only from visible matter, from matter that emits or absorbs light, the numbers did not add up. Galaxies should not rotate the way they do. The stars in the outer regions of a galaxy, according to calculations based only on visible mass, should orbit more slowly than the inner stars, exactly as the outer planets of the solar system orbit more slowly than the inner ones. But observational data showed that the rotation curves of galaxies were surprisingly flat, with the outer stars rotating at speeds much higher than expected. Something was providing additional mass, gravitational mass without light emission, that profoundly altered the dynamics of the entire system. The structure we described, all that elegant geometry, all that hierarchy of patterns, would be much simpler, much more easily explainable, much closer to what naive models predicted, were it not for the presence of an ingredient that permeates everything, but that we still cannot detect directly, a component that amplifies gravitational effects far beyond what ordinary matter alone could produce. The missing mass has a name. It is not a name that describes what it is, because we still do not know what it is. It is a name that describes only what it is not: dark matter. The word dark here does not mean gloomy, does not mean dangerous, does not mean devoid of beauty. It simply means that it does not interact with light in the way that anything familiar to our daily life interacts. It does not emit photons. It does not absorb photons. It does not reflect photons. For the instruments we have built over centuries of astronomy, instruments all fundamentally based on detecting electromagnetic radiation, dark matter is simply transparent. It is like trying to catch water with a net made of light. And yet it is here, around us, permeating this planet right now as you hear these words. Calculations suggest that in every cubic centimeter of space around the solar system, there are hypothetical dark matter particles passing in all directions, incessantly, like a rain that passes through walls, that passes through bodies, that passes through everything without leaving any trace. And this radical invisibility is exactly what makes dark matter so disturbing and so fascinating at the same time. Because the universe has taught us that what we do not see can be much more important than what we do see. To understand why dark matter works as a gravitational amplifier, one must revisit the geometry that physics teaches us about how gravity behaves at cosmological scales. Imagine a spiral galaxy like the Milky Way. From the center outward, there are stars, gas, dust, planetary systems, and all this material moves in orbits around the galactic nucleus. If all the mass were concentrated at the center, or if at least most of the mass decreased progressively as we move away from the center, we would expect orbital velocities to also decrease as we move away. This is exactly what happens in the solar system. Mercury, the planet closest to the Sun, orbits at a speed that in comparative terms is much higher than that of Neptune, the most distant planet. The reason is simple. Almost all the mass of the solar system is in the Sun, and gravity weakens with the square of the distance. But galaxies do not do this. Galactic rotation curves, which are graphs showing orbital velocity as a function of distance from the center, should drop smoothly as we move away. Instead, they remain essentially flat. The stars at the peripheries of galaxies orbit at almost the same speed as the stars in the interior. This is only possible if there is sufficient mass distributed throughout the entire extent of the galaxy, including far beyond where the visible stars end, and it is not a modest amount of hidden mass. The most widely accepted models currently suggest that for every unit of ordinary baryonic mass, the matter that forms stars, planets, gas, and dust, there is approximately 5 times more mass in dark matter, 5 to 1. The Milky Way we see, all that luminous band that cuts across the night sky, is only a smaller fragment of the true gravitational weight of the galaxy. The amplification mechanism is elegant in its brutality. Dark matter forms what cosmologists call halos, approximately spherical three-dimensional structures that surround and permeate visible galaxies. The dark matter halo of the Milky Way extends far beyond the luminous disk we can observe. While the visible stellar disk has a radius of approximately 50,000 light-years from the center, the dark matter halo may extend for perhaps 200,000 light-years or more, creating an invisible volume that is genuinely immense compared to the bright structure we associate with the galaxy. And it is within this halo that the solar system finds itself, immersed in dark matter like an air bubble inside water. The analogy that perhaps best captures this idea is that of an iceberg. The visible part above the surface is real. It is impressive. It is what the eyes capture, but the mass that structures, that keeps stable, that determines the behavior of the iceberg as a whole is hidden below the waterline. The Milky Way is the tip of the iceberg. The dark matter halo is the submerged mass that determines how the system moves, how it responds to disturbances, how it maintains its shape over billions of years. For the solar system specifically, the presence of the dark matter halo has implications that go beyond the abstract. The local density of dark matter, that which permeates the space immediately around our solar system, has been estimated by various models and indirect measurements. The values converge around a fraction of a gram per cubic centimeter of space, a number that seems tiny but that, integrated over the immense volume of the halo, represents a colossal mass. The entire solar system moves through this invisible mist of dark matter while orbiting the galactic center, completing one orbit approximately every 225 million years, in a journey we call the galactic year. This translation of the solar system through the dark matter halo is not neutral. Some speculate that variations in the local density of dark matter as the solar system crosses different regions of the halo could have subtle effects on the Oort Cloud, that sphere of distant comets that marks the broadest outer limit of the solar system. If the density of dark matter fluctuated enough in certain regions, it could gravitationally disturb the orbits of bodies in the Oort Cloud, sending comets toward the inner solar system with periodicities that may be imprinted in Earth's geological record. It is a speculation still debated, but it is the kind of speculation that reveals how the invisible can have profoundly concrete consequences. The visible manifestations of dark matter are, by definition, indirect. We never see dark matter itself. What we see are its effects on what is visible. The flat rotation curve of galaxies is the most fundamental of these evidences. But there are others that have become crucial tools for mapping the distribution of dark matter in the universe. The most visually spectacular of them is gravitational lensing. Einstein taught us that mass curves space-time and that light follows the curvatures of space-time. This means that when light from a distant object passes near a large concentration of mass, it is deflected, exactly as light is deflected when passing through a glass lens. Very massive galaxies or clusters of galaxies function as natural gravitational lenses, distorting and amplifying the image of even more distant objects that are behind them from our point of view. The phenomenon manifests in different ways depending on the geometry of the alignment. When the alignment is almost perfect, the light from a background galaxy spreads into a complete ring around the lensing galaxy, a ring we call an Einstein ring, in honor of the physicist who predicted the phenomenon. When the alignment is partial, luminous arcs form multiple and deformed images of the background object. And when the mass disturbances are more subtle and diffuse, we have what is called weak lensing, which does not produce dramatic individual distortions, but imprints a measurable statistical deformation on the shapes of millions of background galaxies, a signal that can only be extracted by analyzing enormous populations of objects. What gravitational lensing revealed is that the mass distribution that curves space-time and distorts light does not correspond to the luminous mass distribution. Galaxy clusters have more gravitational mass than their visible stars and gas can explain, and this extra mass, this mass that curves light without emitting light, traces contours that only make sense if there are large amounts of invisible matter distributed in specific ways. The Bullet Cluster, a system of two galaxy clusters that collided with each other, became one of the most cited cases because it clearly showed that the gravitational mass and the baryonic mass separated during the collision. The hot gas, which interacts electromagnetically and was slowed by the gas of the other cluster, was left behind, while the dark matter, which does not interact this way, passed through the other cluster without breaking, carrying with it the gravitational center of each cluster. You do not need to look at distant galaxy clusters to feel the weight of dark matter in your experience of the world, although the connection is too abstract to be direct. Think of the night sky. Every star you see there is in the Milky Way, and the Milky Way has the shape it has, maintains the cohesion it maintains, rotates the way it does because of the dark matter halo that permeates and surrounds it. Without dark matter, the galaxy as we know it would not exist in the form it exists. The large-scale structures of the universe, those filamentary webs of superclusters separated by vast voids, formed from primordial disturbances that dark matter was the first to gravitationally collapse, because it did not need to wait for the cosmic background radiation to dissipate enough for baryonic matter to collapse on its own. Dark matter was the scaffolding, the structural framework on which visible matter settled to form stars, galaxies, and planets. And now the sun rises every day over a planet that orbits a star, that orbits the center of a galaxy, wrapped in something we do not see, and the balance of this entire system depends on this invisible in ways we still do not fully understand. There is a disturbing beauty in this. The apparent stability of the solar system, the regularity of the seasons, the rhythm of eclipses, the predictability with which the planets appear in the night sky, all of this exists within a much larger context of forces we can barely characterize. We are like inhabitants of a cabin in the interior of a forest, aware of every corner and plank of the cabin, but with only a partial understanding of the forest that surrounds it, of the forest that determines the climate, the resources, the risks, and the very possibility of the cabin's existence. The theoretical candidates for the identity of dark matter have names that reveal much about the history of physics over the last century. WIMPs, an English acronym for weakly interacting massive particles, were for decades the favorites of theorists. They would arise naturally from extensions of particle physics like supersymmetry, which proposes that each known particle has a symmetric partner not yet detected. WIMPs would be stable, massive enough to be gravitationally relevant, and would interact with ordinary matter only through the weak force and gravity, which would explain why they are so difficult to detect. Sophisticated experiments deep in mines protected by rock against cosmic radiation have searched for decades for the signature of WIMPs colliding with atomic nuclei of xenon or germanium detectors. So far, silence. Axions are another candidate. Hypothetical particles much lighter than WIMPs, originally proposed not to solve the dark matter problem, but to solve an inconsistency in neutron physics. If they exist in large quantities, axions could convert into photons in the presence of intense magnetic fields, and specific experiments search for this conversion. There are also sterile neutrinos, hypothetical cousins of the known neutrinos, but that would not even interact through the weak force, and primordial black holes formed in the extremely young universe that could have masses varying across many orders of magnitude and that escape most forms of detection. Each name carries with it decades of theoretical work, of experiments designed and conducted, of hopes lit and frustrated. What remains constant in this story is the tension between the strength of the gravitational evidence and the absence of direct evidence. The effects of dark matter on the structure of the universe are so clear, so measurable, so consistent with each other, that rejecting the existence of some kind of non-baryonic matter would require rewriting gravitation in a way that no proposed alternative has managed to do satisfactorily. And yet decades of direct searches have found nothing. This creates a peculiar situation in physics. One of the most robust pieces of evidence in modern science points to something whose nature remains completely mysterious. The solar system then floats within a halo of invisible matter, within a galaxy whose real weight is dominated by something we do not see, within a universe whose composition is mostly opaque to our instruments. And this floating seems stable. The sun will rise tomorrow. The planets will follow their orbits. The comets will return with the punctuality that astronomers calculate. But this stability is an illusion of temporal scale. Viewed on scales of billions of years, the galaxy oscillates, the dark matter hollow breathes, and the very structure on which this apparent regularity rests is subject to forces that no short-term prediction can fully capture. The equilibrium is real, but it is the equilibrium of a spinning top which seems motionless but depends on constant spinning to maintain its posture, and which will topple when the spin slows enough. There are moments when the top stops spinning, not suddenly, not with a visible collapse, but with a slowness so profound that no human generation would be able to witness the before and after in a single breath. What we call cosmic stability is, in truth, an average between agitations that last longer than our civilization can imagine. And this average, when disturbed, does not return to the same point. It finds a new equilibrium different from the previous one, bearing the marks of what happened like scars engraved in the geometry of the space we inhabit. The solar system crosses the galaxy in a movement that is not a straight line. It is a long, smooth curve that oscillates above and below the galactic plane with a periodicity of tens of millions of years. In the moments when this trajectory plunges deeper toward the dense plane of the Milky Way, everything changes. The density of stars around increases. The density of gas increases. The gravitational disturbances that reach the Oort Cloud grow in intensity and frequency. What was an occasional rain of comets becomes something closer to a storm. There is a hypothesis that astronomers call the galactic perturbation theory, and it connects these periodic plunges into the galactic plane with mass extinctions recorded in Earth's fossil record. The idea is that when the solar system crosses regions of higher density, gravitational disturbances destabilize trajectories that remained untouched for eons. Objects that lived in peaceful orbits at colossal distances from the Sun receive a subtle push that over millennia converts them into projectiles. Some of these projectiles enter the inner solar system, some reach the rocky planets, some reach the Earth. The word hypothesis here is important. The correlation between galactic orbital cycles and mass extinctions is debated, contested, continuously refined. But the underlying mechanism is not speculative. The gravitational disturbances that reach the Oort Cloud are real, measurable in their effects, and the periodicity of the solar system's plunge into the galactic plane is a solid astronomical fact. What remains open is the magnitude of the biological effects, the precision of the temporal correspondence. The question of whether the signal in the fossil record is robust enough to support the interpretation the hypothesis demands. The disturbance begins almost imperceptibly. A star that passes at a distance still enormous by human standards, but small by interstellar standards, applies a gravitational force on the Oort cloud that accumulates over hundreds of thousands of years. It is like very slowly bending a piece of metal. There is no immediate rupture. The material gradually deforms until, in a moment that does not announce its arrival, the threshold is crossed. An orbit that was stable for billions of years becomes unstable. The object begins to fall toward the Sun. This fall is not an event of days or months. It is a journey that can last millions of years. The object goes from a gigantic orbit to an orbit that eventually brings it to the inner solar system. During this journey, it can be disturbed again, deflected, accelerated, decelerated. It can be captured in a long-period orbit that will bring it back repeatedly over eons. It can, under specific circumstances of orbital geometry, find a path that puts it on a collision trajectory with one of the inner planets. What astronomers call long-period comets are exactly these objects, visitors that arrive from deep space that have never passed through the inner solar system before, or that passed so long ago that they carry no observable memory of previous visits. When a long-period comet is first detected, astronomers look at its orbit and read in it a history of accumulated disturbances, of altered trajectories, of forces applied at immense distances. The comet is, in this sense, an archive. Its orbit is a letter sent from regions of space that no human instrument has ever observed directly. Humanity began observing these visitors with systematic instruments relatively late. For most of history, comets were sky events that arrived without warning and departed without understood explanation. The periodicity of some was recognized over time, orbital mechanics was gradually mapped, and what was once omen became measurable data. Today, networks of automated telescopes sweep the sky night after night, building catalogs of moving objects, calculating orbits, flagging any trajectory that approaches the Earth dangerously. But there is a fundamental limit in this vigilance. Long-period comets, those that arrive from the Oort cloud, for the first time come from any direction in the sky. There is no way to know where to look. They only become detectable when they are already close enough to develop the coma, the cloud of gas and dust that reflects sunlight and makes them visible. And when detected, the time available for any response is measured in months or a few years, not decades. The geodesy of the inner solar system is well mapped, but the outer frontier remains essentially opaque. The dark matter that surrounds the solar system does not only distribute its gravitational influence in a static and constant way. There are models that suggest dynamic structures in this halo, density variations that the solar system crosses along its galactic orbit. If the halo is not perfectly uniform, then there are moments when the solar system plunges through regions of higher dark matter density and moments when it crosses more sparse regions. These variations, however subtle, translate into variations in the total gravitational force acting on the objects of the outer solar system. A proposed model to connect dark matter and comet disturbances suggests that filaments or concentrations of dark matter could act on the Oort cloud in a manner analogous to the passage of nearby stars, applying gravitational disturbances that destabilize orbits. The speculation here goes beyond what current data can confirm, but the physical mechanism does not violate any known principle. Dark matter interacts gravitationally. If it is distributed non-uniformly, its gravitational interaction with the Oort cloud would also be non-uniform over time. What makes this idea fascinating is not its confirmation, which does not yet exist, but what it would imply. It would mean that dark matter, this completely mysterious substance that dominates the weight of the galaxy, would have left traces in Earth's biological record. That mass extinctions, that the evolution of living beings, that the very history of life on the planet would be in some way linked to the properties of something we cannot see, directly detect, or fundamentally understand. The Earth as an archive of cosmic events whose nature still escapes comprehension. While you rest somewhere on the periphery of the solar system, an object that has not been disturbed since the Earth did not yet exist is now receiving the accumulation of a gravitational force applied eons ago. Its orbit is changing in increments smaller than any instrument could measure in a single observation. The threshold that separated it from stability and fall is being approached with the patience that only geological time possesses. At some moment, this threshold will be crossed. The countdown for a journey that will last millions of years will have begun without witnesses, without announcements, in the absolute silence of interstellar space. But the phenomena that emerge from the disturbances of the outer solar system are not only projectiles, they are also structures. When comets plunge into the inner solar system and pass near the Sun, the heat sublimates the icy surface, releasing gas and dust that distributes along the orbit. Over time, these debris form dust streams that remain stable for centuries or millennia, marking the path where the comet passed like a luminous trail that the Earth periodically crosses. Every meteor shower that occurs in the night sky is the Earth crossing one of these trails, burning in the atmosphere the fragments left by a visitor that came from deep space. The most regular meteor showers correspond to well-established debris streams, and astronomers know the comets that generated them. But there are meteor showers of unknown origin, debris streams whose original comet either completely fragmented or has not yet been identified. Each of these streams is a persistent phenomenon, a dynamic structure that exists in real space, not only as a concept, but as a physical distribution of matter that the Earth crosses with regularity. The Earth's atmosphere itself is a detector of outer solar system events. Every fragment that comes into contact with the upper layers of the atmosphere releases energy, ionizes the air, leaves trails of light and matter that modern instruments capture in extraordinary detail. The network of all sky cameras that covers growing parts of the globe records hundreds of entries per night, calculating velocities, trajectories, and spectral compositions in real time. The frequency of these entries, when analyzed over decades, reveals patterns, some expected corresponding to known showers, others anomalous, indicating arrivals that do not fit the catalogued streams. The distinction between a meteorite of asteroid belt origin and a meteorite of Oort cloud origin is inscribed in the speed at which the object enters the atmosphere and in the chemical composition that spectrometers detect during entry. Objects that come from deeper space arrive faster, with compositions that preserve pristine materials from the beginning of the solar system, matter that was never heated, never altered by solar heat, kept frozen and intact for nearly 5 billion years. These fragments are time capsules. Their analysis reveals conditions that existed even before the Sun was fully formed. What makes the intense mode of the outer solar system qualitatively different from the calm mode is not just the magnitude of the disturbances, it is the difference between a system in dynamic equilibrium and a system that is being pushed through a threshold. In equilibrium, the disturbances cancel out or distribute in a way that does not fundamentally alter the structure of the whole. In the intense mode, the disturbances accumulate, reinforce each other, and the result is a reorganization that does not return to the previous state. The mass extinctions that mark the fossil record are the most dramatic moments of this intense mode recorded in Earth's history, but they are not the only ones. There are periods of increased bombardment that did not reach the point of causing mass extinctions, but that altered the composition of the Earth's surface, that delivered additional organic material and water, that shaped the crust in ways still being investigated. The outer solar system in its most agitated moments is not only a threat, it is also a supplier of matter, of chemical complexity, of ingredients that life may have used. Astronomers measure the history of these bombardments in the craters that cover the Moon, Mercury, Mars, and the moons of other planets. The Earth, with its active geology and erosive atmosphere, quickly erases the marks of ancient impacts. But the Moon is an almost untouched archive, and the pattern of ages of its craters tells a story of variable intensity. There were periods of elevated bombardment, followed by periods of relative calm, followed by new increases. This variation is not random. It has patterns that astronomers try to map, correlate with orbital positions, with passages through the galactic plane, with the dynamic history of the young solar system. The breaking point is a metaphor, but it is also a dynamic reality. There is an orbit that is the last stable orbit. There is a distance that is the last safe distance. There is a trajectory angle that separates the comet that passes through the solar system and moves on from the one that will be captured, that will collide, that will fragment against Jupiter or Saturn before reaching the inner planets. These thresholds are calculable in principle, but the calculation requires knowing precisely the positions and velocities of all relevant objects, and the outer solar system is vastly underestimated in its real population. What telescopes detect is a fraction of what exists. Most of the objects in the Oort Cloud, in the Kuiper Belt, in the space between the stars adjacent to the solar system remain completely unobserved. When astronomers calculate the frequency of impacts, when they estimate the quantity of comets in transit through the solar system at any given moment, they make extrapolations from samples that represent a tiny proportion of the real total. The uncertainties are enormous. The error bars on the estimates cover orders of magnitude. It is a science of inferences built with rigor, but resting on data that is necessarily incomplete. This incompleteness is not a temporary flaw that better telescopes will completely resolve. There are objects small enough that no foreseeable instrument will detect them until they are very close. There are objects on trajectories that cross poorly observed regions of the sky. There is a horizon of knowledge that recedes as we approach, but that never disappears. The solar system exists within a galactic context that is partially opaque, and this opacity is not passing. It is structural. And yet, the phenomena that emerge from this opacity do not happen in isolation. A comet that plunges into the inner solar system does not travel an empty path. It crosses magnetic fields, encounters the solar wind, interacts with the dust that fills interplanetary space. Its fall is modified by forces that are not only gravitational, Its composition is altered by radiation, by collisions with charged particles, by chemical processes that occur when the ice begins to sublimate. The journey from deep space to the inner solar system is a chain of transformations, each stage shaped by the environment the object crosses. The chain of transformations that a comet experiences as it descends from deep space is not only a sequence of physical events, it is a narrative of connection, a report of how objects that existed in isolation for immense eons suddenly find themselves integrated into a living, dynamic system, full of fields and forces and flows that never cease. And this integration reveals something essential about the nature of the solar system as a whole. It is not a collection of separate bodies traveling in parallel orbits. It is a fabric, a set of systems that exchange energy, matter, and influence in ways we have only begun to map clearly in recent decades. The most fundamental partner in this exchange is the Sun, not only as a source of gravity, which is what we normally imagine when we think of the central star, but as a continuous emitter of energy in all its forms. The solar wind, which we have already mentioned in its most basic structure, is actually an extension of the solar corona, the outer layer of the Sun's atmosphere that reaches temperatures of several million degrees. The exact mechanism by which the corona stays so much hotter than the Sun's visible surface continues to be one of the unsolved problems of astrophysics. But the result of this heating is the constant flow of plasma that fills the entire heliosphere. This plasma does not travel in a straight line. It spirals outward following the lines of the solar magnetic field, creating a structure called the Parker spiral, named after the physicist who predicted it mathematically before any probe could confirm its existence. The spiral forms because the Sun rotates on its own axis while ejecting particles, and the result is that the interplanetary magnetic field has the shape of an immense whirlpool that extends across the entire extent of the heliosphere. Any object that enters the inner solar system crosses this whirlpool. A comet coming from outer regions begins to feel the pressure of the solar wind long before it begins to shine. The ice molecules that sublimate from the nucleus surface are ionized by the Sun's ultraviolet radiation and by the bombardment of charged particles, and these ionized molecules are then dragged by the interplanetary magnetic field. That is how the ion tail of a comet forms, that bluish tail that always points directly away from the Sun, regardless of the direction the comet is moving. The dust tail, on the other hand, follows a slightly different curve because the dust particles are not charged and respond mainly to radiation pressure. The two tails, therefore, tell different stories about the two mechanisms through which the Sun influences the objects that visit it. This interaction between the comet and the Sun is a feedback cycle of delicate nature. As the comet loses mass in the form of gas and dust, the cloud of material around it, called the coma, grows and expands. A large coma absorbs more solar radiation, which accelerates the sublimation of ice, which further expands the coma. At the same time, the loss of mass slightly alters the comet's trajectory, because sublimation does not occur uniformly across the entire surface. The regions illuminated by the Sun lose material more intensely, and this jet of gas acts as a weak but real thruster. Over multiple passages through the inner solar system, these non-gravitational effects accumulate. Comets with orbital periods of decades, like Comet Halley, whose period is approximately 75 years, have their orbits progressively modified by these subtle forces. Astronomers need to include these effects in orbital calculation models for predictions to be accurate. The behavior of the system in the short term, say in the coming decades, is reasonably predictable for the objects we already know. The orbits of the larger planets are stable within very narrow margins. The position of Jupiter 100 years from now can be calculated with sufficient precision for space mission planning. The periodicity of well-studied comets can be predicted with an error margin of days or weeks, which is remarkable given the size of the distances involved. But this predictability has structural limits that become evident when we extend the time horizon to centuries and even more to millions of years. The solar system, like any dynamic system with many interacting bodies, exhibits what mathematicians call sensitivity to initial conditions. This means that tiny differences in the current state of the system, differences that would be below the capacity of any measuring instrument, amplify exponentially over time. Computer simulations of the solar system that advance time by hundreds of millions of years show that Mercury's orbit is technically unstable on these scales. There is a small but not negligible probability that, at some point within the next 5 billion years, Mercury will be ejected from the solar system or enter a trajectory that results in collision with Venus or the Sun. It is not a certainty. It is a possibility that emerges from the chaotic nature of gravitational interactions over sufficiently long timescales. In the regions above and below the solar system, the relevant timescales are even more extensive. The Oort cloud, if it exists with the structure we imagine, was shaped by gravitational disturbances that accumulated over billions of years. The stars that passed relatively close to the Sun throughout the history of the galaxy left marks on the distribution of objects in this region. The passage of a star at a distance of a few tens of thousands of astronomical units, which is not a rarity on the time scale of the galaxy, is enough to significantly disturb the orbits of objects in the Oort cloud. Some of these disturbances send objects into the inner solar system. Others eject objects into interstellar space. The flow of comets we experience today is, in part, the result of disturbances that occurred tens or hundreds of millions of years ago. And when we think in scales of hundreds of millions of years, we also need to consider the movement of the solar system itself through the galaxy. The Sun orbits the galactic center with a period of approximately 225 million years, a period sometimes called the cosmic year or galactic year. But this orbit is not flat in the plane of the galaxy. The Sun oscillates up and down, above and below the galactic plane, with a period of tens of millions of years. When the solar system plunges closer to the galactic plane, it encounters higher densities of matter, more intense gravitational fields, and possibly dense molecular clouds. There are hypotheses that try to correlate these passages through the galactic plane with periods of mass extinction on Earth, suggesting that gravitational disturbances at those times would send more comets into the inner solar system, increasing the probability of impacts. The correlation is not established with certainty, but the underlying mechanics is plausible and continues to be investigated. This connection between the solar system and the galaxy is what makes the question of what exists above and below our solar system so much richer than it seems at first. We are not asking only about the geography of nearby space. We are asking about the forces that shape the history of the solar system over geological time. We are asking about the influences that arrive from distances we cannot even probe directly. We are asking ultimately about the limits of what we can know and predict about the place where we exist. These limits are real and have a specific structure. There is the instrumental limit, which is the horizon beyond which our telescopes simply do not have enough sensitivity to detect small and cold objects. There is the temporal limit, which is the time window within which we can make reliable predictions before dynamic chaos erodes the precision of our models. And there is the conceptual limit, which is the possibility that phenomena or structures exist for which we do not yet have adequate vocabulary, categories of objects or processes that we have not yet included in our models, because we do not yet have evidence of their existence. The hypothetical planet that some astronomers postulate based on the orbital anomalies of trans-Neptunian objects is a perfect example of this third type of limit. It may be that the best explanation for the observed patterns is the existence of a massive undetected object in the outer regions of the solar system. It may be that the explanation is observational bias, that we more easily detect objects in certain parts of the sky, and that the patterns we see are artifacts of our way of looking, not characteristics of space itself. It may be that the explanation is something completely different, some effect we do not yet understand. Scientific honesty requires that we keep all these possibilities open until additional evidence allows discrimination between them. There is a peculiar beauty in this state of structural uncertainty. It is not the beauty of ignorance, which is simply the absence of knowledge. It is the beauty of a system that is comprehensible enough that we can ask precise questions, but complex enough that the answers continue to be surprising. We understand orbital mechanics deeply enough to send probes to distances of tens of astronomical units and hit targets the size of a city, and at the same time we do not know for certain how many objects exist in the regions beyond Neptune. We do not know if the Oort Cloud has the structure we imagine. We do not know if there is a massive undetected planet at a distance that would be, in human terms, incomprehensibly vast. This combination of competence and humility is perhaps the most appropriate posture before a system of this magnitude. The solar system is not a solved problem that only awaits confirmation of details. It is an object of active investigation whose frontiers continue to recede as we advance. Every mission that sends data from deep space, every telescopic survey that catalogs new objects in the outer regions, every computational model that tests hypotheses about the formation and evolution of the system reveals not only answers but also new questions we could not have formulated without previous knowledge. And at the center of all this, above and below this entire structure of layers and frontiers and interactions, when the mind quiets enough to stop enumerating details and simply begins to contemplate the whole, something emerges that is not exactly a thought. It is more like a perception. The perception that behind all this complexity, behind the spiral magnetic fields and the chaotic orbits and the clouds of icy objects and the galactic disturbances and the limits of knowledge, there is something that sustains all of this, something that is at the same time simpler and more profound than any of the phenomena we have described. Something that is not a force nor a particle nor an equation, but that the phenomena somehow express. This something has not yet been named here. This something that has not yet been named perhaps does not need a name to be recognized. Perhaps language, with all its capacity to name stars and measure interstellar distances and describe the curvature of space, finds here a limit that is not a flaw but an invitation for the mind to stop naming and simply begin to perceive. And what it perceives when it stops is a kind of coherence, a consistency that runs through all scales, from the grain of dust that orbits the sun at a distance of tens of thousands of astronomical units to the galaxy that extends for 100,000 light years above and below our plane of existence. This coherence is not magic, but it is also not reducible only to physics. It is the fact that the same laws that govern the formation of a dewdrop on a blade of grass are the laws that determine how an interstellar gas cloud collapses to form a star. Gravity has no preferences. Thermodynamics does not choose scales. And that is exactly why the universe has the shape it has, both here nearby, where we can almost touch with the instruments we have built, and out there, where we only arrive through models and deductions and a certain dose of disciplined imagination. What exists above and below our solar system is, in part, a question of feedback. The processes that structure this region of the cosmos are not linear. They do not follow a simple sequence of cause and effect. They fold back on themselves, amplify and moderate in cycles that can last tens of millions of years. When the solar wind blows more intensely during periods of higher solar activity, it pushes the heliosphere further out, compressing the space that interstellar matter can reach. This compression alters the pressure gradient at the edges of the system, which in turn affects how energetic particles from the galaxy infiltrate our local space. And these particles, by interacting with the Earth's upper atmosphere, influence the formation of condensation nuclei in clouds, which can affect the global climate over geological timescales. The Sun changes the heliosphere changes what enters the system, what enters the system changes the Earth, and the Earth is part of the solar system that generates the Sun that changes the heliosphere. A cycle within a cycle within a cycle. But it is not only the amplifying processes that sustain this structure, there are also the stabilizers, the mechanisms that prevent everything from collapsing or dispersing irreversibly. The very mass of the Sun, by curving the space around it, creates a gravitational basin that keeps the planets in their orbits over billions of years with a precision that defies human intuition. The Oort Cloud, that spherical shell of icy objects that extends to halfway to the nearest star, is stabilized by a delicate balance between the Sun's gravitational attraction, which keeps it bound, and the gravitational disturbances of the galaxy, which continuously reorganize its orbits without completely dissolving it. It is a dynamic stability, not a static rigidity. An equilibrium that moves, that oscillates, that breathes, but that persists. The molecular and compositional dimension of all this is perhaps the most underestimated when we think about space. We tend to imagine the interstellar void as exactly that, a void. But what exists above and below our solar system, in the space between it and the next significant galactic structure, is traversed by molecules. Molecular hydrogen, the simplest and most abundant of all compounds, floats in immensely low but not negligible densities. Carbon monoxide exists in these regions, as does water in the form of ice-coating dust grains. Simple organic compounds, the fundamental building blocks of chemistry that eventually, under the right conditions, can lead to life, have wandered through the interstellar medium for billions of years before any star formed to host them. When we think about the Oort Cloud above and below and around us, we are not thinking only of ice rocks. We are thinking about reservoirs of primordial chemical matter preserved at temperatures near absolute zero that guard the compositional memory of the nebula that gave rise to our solar system about 4.5 billion years ago. The comets that occasionally fall from the heights of these regions and plunge toward the Sun are messengers of this memory. They bring water, they bring carbon compounds, they bring silicates and sulfides and sometimes amino acids, the building blocks of the alphabet of life. The chemistry that exists above us is not separate from the chemistry that exists within us. It is, in a very literal sense, the same chemistry, just in different states, at different scales, at different ages. The solar system, seen as an integrated system, is a structure of interdependencies that extends far beyond the planets and moons we normally evoke when we imagine it. It begins with the Sun, which is not only a source of light and heat but a magnetic field generator, an emitter of particle wind, and a gravitational organizer of everything around it. This Sun is wrapped by the planets, which in turn are wrapped by their moons and rings and their own magnetic fields. Around the planets, the asteroid belt and trans-Neptunian objects form a second layer of structure, and around all of this, like an invisible and immense cocoon, the heliosphere pulses with the rhythm of solar activity, expanding and contracting over 11-year cycles that reflect variations in the Sun's magnetic field. Beyond the heliosphere is the heliopause, the frontier where the solar wind loses the battle against the interstellar wind. And beyond that frontier, within the local interstellar cloud that permeates our immediate cosmic neighborhood, the solar system continues to be a system, continues to exert gravitational influence, continues to define a region of space as distinct from the rest. The Oort Cloud is part of the solar system. It obeys, however tenuously and vulnerably, the sun's attraction. It is the outer limit, the outermost skin, the place where the solar system ends not abruptly but gradually, like a sound that dissolves until it is no longer possible to distinguish it from silence. The emergence of complex patterns from simple rules is perhaps the most contemplative aspect of everything that exists in these regions. Gravity obeys a simple equation, the proportion between the mass of two objects and the square of the distance between them. This equation, applied repeatedly to billions of objects over billions of years, produces galactic spirals, solar systems, planetary rings, comets with elliptical orbits that extend for light years and return to their point of origin with a punctuality that the ancients saw as divine. There is nothing in the equation of gravity that predicts comets, and yet comets inevitably emerge from it, like poetry emerges from the letters of the alphabet, like a symphony emerges from musical notes. The same generative simplicity governs the magnetic structure of the system. The sun's magnetic field, as it is carried by the solar wind into space, wraps into a spiral that astronomers call the Parker spiral, named after the physicist who predicted it decades before it could be directly observed. This spiral emerges from the simple laws of electromagnetism applied to the motion of an expanding plasma, and this spiral, by interacting with the magnetic fields of the planets and with the interstellar magnetic field, creates interference patterns that influence where and how cosmic particles penetrate the system. Pattern within pattern within pattern, all emerging from rules that fit in a few lines of mathematics. At bottom, what exists above and below our solar system is simply the expression of continuity, the idea that there is no place where the universe ends and another place where the solar system begins. Everything is continuous. The Oort Cloud is not a wall, it is a transition. The heliopause is not an absolute frontier, it is a region of dynamic equilibrium. The local interstellar medium is not a void separate from our system, it is the environment within which our system exists and breathes and moves. When we reconnect each element of the previous parts to this idea, what we see is always the same pattern. The inclined orbits of trans-Neptunian objects reveal the continuity between the planetary disk and the outer cloud. The gravitational disturbances of nearby stars reveal the continuity between our system and the galaxy. The chemistry of comets reveals the continuity between interstellar space and the molecules of life. The spiral magnetic field reveals the continuity between the Sun and the interstellar medium. In all cases, what seemed like a frontier is actually a transition zone. What seemed like a separation is actually a connection. And in this continuity there is something that quiets, something that, when truly perceived, dissolves the sensation that we are small and isolated in an indifferent universe, because indifference presupposes separation. It presupposes that there would be a universe here and us there, looking at it from outside. But there is no outside. We are made of the same atoms that travel in the Oort Cloud. Our bodies carry oxygen that was forged in stars that exploded billions of years before the sun existed. Our blood contains iron that is the same iron that exists in the cores of planets and in the interstellar dusts that float above and below the plane where we live. Continuity is not a metaphor, it is a chemical, physical, and gravitational description of reality. And when this reality is felt, not just intellectually understood but truly felt, it transforms the relationship with the silence of the night. The solar system continues its movement while you rest. The heliosphere pulses. The comets trace their long and silent orbits. The Oort Cloud remains suspended in the delicate balance between the sun's attraction and the gentle touch of the galaxy. You are safe. You always have been. The universe cares for you with the same attention with which it keeps the stars on their paths. Not because you asked, but because you are part of the structure that sustains everything. Everything is in order. The same laws that curve the orbit of a distant comet regulate the rhythm of your heart right now. The same gravity that keeps the Earth on its path around the Sun keeps you gently settled in this moment, in this place, in this instant of stillness. While you rest, the heliosphere continues breathing with the Sun. While you rest, the icy objects of the Oort Cloud continue their silent orbital dance. While you rest, the spiral magnetic field continues extending through interstellar space, telling the story of where we came from. You are part of this. You always have been. Your eyes, which have so often looked at the sky, can close now. The sky continues, the stars continue, the space above and below, that vast and silent space full of invisible structures, continues existing with or without observers. But tonight it existed for you. You walked through it with imagination. You touched its frontiers. You felt the thickness of the void, which is not truly void, but an abundance of scales that our everyday perception was not made to encompass. And now it is time to let this be big without needing to understand it. It is time to let the mind rest like a water surface that stops being agitated and slowly, very slowly becomes a perfect mirror. Nothing needs to be solved tonight. Nothing needs to be understood. You are safe. The universe cares for you. Everything is in order. There are comets traveling now in arcs that take thousands of years to complete. There is interstellar dust floating in the heights above every atmosphere. There is a balance that has been maintained for billions of years and that will continue to be maintained while you sleep, while you dream, while you breathe ever more slowly and deeply. Each breath you release is air that was part of the earth for eons before you existed, and that will continue existing after you wake up tomorrow. You borrow the universe for a moment, and the universe, generous, continues. Let your shoulders sink, let your thoughts pass like objects in eccentric orbits that appear briefly and move on. Let the silence be vast. You are part of the solar system. You are inside the heliosphere. You are inside the galaxy. You are inside the universe. And the universe is, in some way we do not yet fully know how to name, inside you. Sleep now. The universe continues its silent dance, and we rest in its embrace. Thank you for walking with me tonight. Sleep well.